In this video, we are going to conclude talking about the topics of chapter 4. We're going to focus on isomerism of organic compounds. Isomerism refers to the formation of isomers, and isomers by definition are going to be molecules with the same formula, meaning chemical formula, but they have different arrangement of atoms in a molecule, and this different arrangement of atoms is going to lead to these molecules to have different properties. When it comes to isomers, for the purposes of this class, you guys need to focus on only constitutional isomers, also known as structural isomers, and from the stereoisomers, only what are diastereomers and what are enantiomers. We are going to explore each one of these groups of isomers. Let's first talk about constitutional isomers. Constitutional isomers, which are also known as structural isomers, are going to be compounds that differ in the way in which the atoms are connected to one another. Remember that the two molecules that we are comparing actually have the same chemical formula. Here we have several examples of constitutional isomers. So we can see here that both of these alkynes are going to be structural isomers. They both have the chemical formula C6H10. These skeletal structures, if I write in the carbon atoms, let's put it right here. There's a CH2 right here. There's the carbon, CH2, CH3. We can observe, let me also write it for the other one. This is a CH, this is a carbon, CH2, 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 CH3. We can observe that both molecules have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5, 6 carbons. And then 10 hydrogens. 3 plus 2, that's 5. 3 plus 2, that's another 5. That's where the H10 comes from. 1 plus 2, that's 3. Plus another 2, that's 5. 2 and 3, that's another 5. We have the 10 hydrogens in the other molecule. Now, when it comes to these two molecules, one of the ways that we can actually identify that they are going to be structural isomers of each other is that even though they have the same chemical formula, they will have different names. So overall, we can observe that the molecule on the left is 3-hexyne, while the molecule on the right is 1-hexyne. So if you're given names of molecules and you're able to draw them, you can actually draw the structures and determine if they have the same chemical formula, that they are structural isomers of each other, or constitutional isomers, which is the same thing. Here, we have two molecules. They share the chemical formula C4H8. On the left, we have cyclobutane. And we can observe how this molecule has 4 carbons and 8 hydrogens. The molecule on the right, this is 1-butene. And if I write in the carbons and hydrogens, we can see that both molecules share that C4H8, and then they have different attachment of the atoms. These two molecules are a little bit more complex. They have the chemical formula C5H10O. And while at this point, you guys cannot name these, at least you can identify the functional groups that you have here. The molecule on the left is an ether. The molecule on the right is a ketone. So if you're given structures of ethers and ketones and they have the same chemical formula, they're going to be structural isomers of each other. So the take-home message here is that for constitutional isomers, same chemical formula, but the connectivity of the atoms is going to be different. Let's now move on and explore stereoisomers. When it comes to stereoisomers, similar to structural isomers, these two molecules that we are going to be comparing have the same chemical formula. But interestingly, they are not structural isomers because the atoms in a stereoisomer are actually bonded in the same sequence. It's just that they're different in the way they are arranged in space. When two molecules that are organic compounds, you have them and they're mirror images of each other. And in addition, they are non-superimposable and they're chiral, then the relationship that they have is specifically called enantiomers of each other. So these two molecules that we have here as an example are going to be enantiomers of each other. So what does this mean? The two molecules need to have the same chemical formula, but that's a given because they're stereoisomers. The molecules need to be chiral. Chiral means that the atom that is in the middle, which we are focusing on carbon, let me just write it in, needs to have 4 different groups around itself. So that's what chiral means. 4 different groups around carbon. Now, if that is the case, and the molecule has its mirror image, understand that those two molecules are non-superimposable. So what that means is that if you try to overlay them, as you can see, only 2 out of the 4 atoms around carbon, which the carbon atoms are right here, are going to line up. So if you have a molecule like this, understand that their relationship is going to be enantiomers of each other. In general, when it comes to the concept of stereoisomers, it is important that you guys know how to identify chiral carbons within an organic compound. So as an example, I'm going to go over molecule A. Molecule A, as you can see, this is an alkane. And in this alkane, I'm going to write in the carbons and hydrogens that are not illustrated by the skeletal structure. So this is a CH, this is a CH3, this is a CH3, this is a CH, this is a CH3. So now I'm going to label the carbon atoms in this molecule with letters. And this is going to be random letters. This is not specified that it needs to be labeled in specifically how I did it. So I'm just going to put a letter A here, a letter B here, a letter C here, a letter D, E here, and a letter E there. This is just labeling the carbon atoms. Then, when you're trying to determine the chiral carbons that you have in a molecule, you need to ask yourself, does my carbon atom have 4 different groups around? So when we look at the letter A, because that carbon has 3 hydrogens, that's not a chiral carbon. When we look at letter B, because that carbon has 3 hydrogens, that is not a chiral carbon. Letter C has the hydrogen. It has this whole group, but because it has a CH3 and a CH3, carbon C is also not chiral. When we look at carbon D specifically is bonded to hydrogen, bromine, a methyl group in this whole part of the molecule. So that means that carbon D is a chiral carbon. And typically chiral carbons, we label them by putting an asterisk next to it. And then letter E, you can see that it's a CH3 because that carbon atom has more than 2 atoms that are the same. That is not a chiral carbon. So what I'm trying to illustrate here is that if this molecule happens to have its mirror image, then the relationship between the 2 molecules is going to be an enantiomer because the molecule actually has a chiral center. Make sure that you explore in molecule B, if the molecule has chiral carbons, how many and where they are located. I'm going to label the carbon atoms in the molecule. So this is carbon A, carbon B, carbon C, carbon D, and carbon E. Make sure that you practice. There's one more of a stereoisomer that you guys need to be familiar with. And those are diastereomers. Even though the concept of diastereomers is actually more extensive, for the purposes of this class, cis-trans isomers, which can only be found in alkenes, is going to be our example of diastereomers for organic compounds. So whenever you have an alkene, understand that that carbon-carbon double bond is actually rigid and cannot rotate. So the groups that are connected to the carbon that are double bonded are actually in fixed positions. So if we look at the molecule 1,2-dichloroethane, there's actually 2 conformations of 1,2-dichloroethene. Sorry, not ethane, ethene. We have the cis conformation of 1,2-dichloroethene and the trans conformation of 1,2-dichloroethene. Whenever you have a cis molecule compared to the trans version of it, the relationship between those 2 molecules is going to be diastereomers of each other. Now, how do I know if my alkene is cis versus trans? Well, if the high priority groups around the double bond are on the same side of the molecule, that means that your molecule is cis. If your high priority groups are going to be in opposite sides of the molecule, that means that the molecule is trans. Since we recently learned how to name alkenes, let's incorporate this knowledge of cis versus trans into the naming of alkenes, in addition to knowing that if you have two alkenes and one is cis and the other one is trans, that they're diastereomers of each other. So I'm going to do one example for you. We have the following alkene. And in this alkene, we can observe that we have the fluorine molecules. So here, the way that we determine if an alkene is cis and trans is in the following way. The first step that you do is that you take your alkene molecule and you divide it in half. Next, you're going to write in the carbon atoms. There's a carbon right here, and there's a carbon right here. The carbon that I have on the left is attached into a fixed position to the fluorine that is pointing up. And since you don't see what is pointing down, and this is a hydrocarbon, that must be a hydrogen. On the right side of the alkene, the carbon atom is attached to a CH2. On the position moving down, that fluorine is locked into position. So this is how we determine cis versus trans. We are first going to look at the atoms connected to the carbon on the left. The way that we determine the priority of the groups for cis and trans configurations is going to be based on atomic number. So this carbon atom is attached to fluorine versus hydrogen. Fluorine, because it has a higher atomic number compared to hydrogen, we consider it a high priority group. Hydrogen is going to be low priority in this case. So that deals with the stuff attached to the first carbon in the carbon-carbon double bond, the one on the left. Let's now look at the carbon on the right. The carbon on the right is connected to fluorine versus carbon. When it comes to the comparison of fluorine versus carbon, fluorine has a higher atomic number, so we label it high. Carbon has a lower atomic number, so we label it low. If we look at this molecule, we can see that our highs and lows are on different sides, because you can see that towards the top of the molecule, we see high, low, and in the bottom, we see low, high. Since our high priority groups and low priority groups are on opposite sides, that means that this alkene specifically is trans. Then we can actually proceed to name this alkene. So when it comes to this alkene, we see that on position 1 and on position 2, we have two fluorines. So this is 1, 2 difluoro. The carbon-carbon double bond is on the first carbon. Overall, in this molecule, we have 1, 2, 3, 4, 5. So the name of the parent chain is pentene. So as you can see, for alkenes, we can even incorporate the concept of how to determine if a particular alkene is cis versus trans. Here we have several examples of cis versus trans. Take a moment and, following the steps that were explained, determine if this alkene is cis versus trans. Let's go over the answer. I take my alkene and I divide it in the middle. I write in the carbon atoms. There's one right here, which towards the top is connected to a CH3. Towards the bottom is connected to a bromine. Here I have another carbon atom, which towards the top is connected to hydrogen, and the bottom is connected to a CH2. So my carbon atom that is on the left side of my double bond, this carbon, I'm comparing bromine versus carbon. Bromine has a higher atomic number, so this is going to be labeled high. Carbon, because it's lower atomic number, is going to be labeled low. Then I move on to the right side of the slide. I can see that for this carbon atom, I'm comparing hydrogen to carbon. Carbon has a higher atomic number. So this group pointing down is going to be labeled high. The hydrogen on the top is going to be labeled low. In this example, we can observe how the lows are on the same side and the highs are on the same side. So for this molecule specifically, this configuration for an alkene is going to be cis, because my high priority groups are pointing in the same direction. Then I can continue just naming this molecule. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. There's only one substituent of carbon 2, which on carbon 2 we have a bromo group. My carbon-carbon double bond is between 2 and 3. So at position 2 is the first carbon in the double bond. Since I have 6 carbon, hex represents the 6 carbons in the parent chain. And since this is an alkene, this is hexene. So that's how you name the following alkene. Be aware that not every alkene needs a cis and tris configuration, but some of them do. Make sure that you practice with the other examples that we have on the slide.